Welcome to the deep dive. Ever think about the unseen superhighways inside your devices? That invisible engine connecting everything from your screaming fast graphics card to your lightning quick storage. Well, that's PCIe, and today we're taking a deep dive into something truly groundbreaking, PCIe 6.0. And look, this isn't just another speed bump, it's really a foundational re-architecture. It's powering the future of AI, supercomputing, and, the massive data centers shaping our world.
That's exactly right, yeah. Our mission for this deep dive is really to pull back the curtain on the why behind this huge transformation. We want to look at the ingenious engineering solutions that made it possible, and maybe most importantly, what this all means for you, whether you're just curious, maybe prepping for a big meeting, or just want to understand the tech that's, shaping everything. We've sifted through a whole stack of industry reports, tech specs, expert analyses, trying to bring you the most important nuggets.
Okay, let's unpack this then. The headline number for PCIe 6.0 is, it's staggering. 64 gigatransfers per second per lane. So that means a full by 16 link can deliver a mind-bending 128 gigabytes per second, unidirectional. That's a lot of data.
It really is.
But here's where it gets really interesting, right? They couldn't just double the frequency like they did in previous generations. So why not? What wall did they hit?
Yeah, it really comes down to fundamental physics. And the very real limits of copper interconnects on circuit boards. If they had just continued with the traditional NRZ signaling that's non-return to zero used in older PCIe gens, it would have pushed the Nyquist frequency up to an impractical 32 gigahertz.
32 gigahertz.
And at those kinds of extreme frequencies, the signal loss over just standard circuit boards, it would have been an astounding 60 to 70 decibels.
Whoa, 60 to 70 decibels. What does that, for our listeners, what does that mean practically? Like how much signal is actually getting through?
Think of it like trying to shout across a packed football stadium during, a rock concert.
Okay, yeah, not much.
Right, almost nothing gets through, clearly. Reliable communication would have been utterly impossible without a complete and frankly economically unfeasible overhaul of materials, design, everything. It was basically a non-starter.
So, brute forcing the frequency was out.
Yeah.
They had to get clever. What was their ingenious workaround?
Precisely. They introduced a real paradigm shift, something called four-level pulse amplitude modulation, or PM4 signaling.
PM4, okay.
Think of it like this. Traditional NRZ is like sending 1 bit per blink light on or light off.
Yeah.
Simple.
Binary.
Exactly. PMM4, though, it can send 2 bits of information in that same blink by using 4 distinct signal strengths. So imagine maybe a dim light, a medium light, a bright light, and a super bright light.
Okay. 4 levels and code 2 bits.
You got it.
Yeah.
And the masterstroke is this doubles the data density without increasing that fundamental 16 gigahertz Nyquist frequency. This allowed PCIe 6.0 to maintain a channel reach how far the signal can travel reliably, pretty similar to PCIe 5.0 even on comparable board materials.
That sounds fantastic. Doubling the data in the same time. But, if you're cramming more information into the same signal, there have to be a catch, right? There's always a trade-off in engineering.
You've hit the nail on the head. There is a critical trade-off. By packing 4 voltage levels into the same space, the same voltage swing that previously only held 2, the vertical separation between those levels gets much smaller.
Okay, so they're closer together.
Right. And that results in a significant degradation of the signal-to-noise ratio, the SNR. We're talking about 9.5 dito beats worse.
Okay, degradation of signal-to-noise ratio. For us non-engineers, what does that really mean? How does it affect this signal?
Think of it like trying to hear a whispered secret in a really noisy room. The secret is much weaker compared to all the background chatter.
Right. Harder to pick out.
Exactly. It makes the PM4 signal far more susceptible to noise, to jitter, to crosstalk from neighboring lanes. And this leads to a much higher raw bit error rate. It just makes more mistakes initially. It also means you need more advanced diagnostic tools, more complex compliance tests. You can't just use the simple eye mask tests anymore to check if the signal's clean enough.
This higher error rate, though, it sounds like a massive problem. For a reliable data bus that's supposed to be the backbone of everything, how on earth did they tackle that without compromising the whole system?
That's the core question, isn't it? How do you get reliability with this inherently higher error rate? PM4 targets something like a 10.6 first bit error rate, 1 error in every million bits, roughly. The solution was to mandate the use of forward error correction, or FEC.
FEC, okay.
But FEC algorithms, they work best or really require fixed-size blocks of data to operate efficiently, and that requirement led directly to the second major architectural shift in PCIe 6.0, adopting something called Flow Control Unit Mode, FLIT mode.
So FLIT mode was a direct consequence of needing FEC. Because, yeah, my understanding is that prior generations used variable length packets. But now, at 64 GTs, it switches to these fixed-size 256-byte FLITs. How does that work? What's actually inside these FLITs?
That's exactly right. Necessity drove the invention here. These 256-byte FLITs have a very precise structure. 236 bytes are for your actual payload, the TLP data. Then you have 6 bytes for data link layer stuff, DLLPs, 8 bytes for a strong CRC error check, and finally 6 bytes specifically for the FEC itself.
Okay, so structured blocks.
Right. But here's where it gets really clever. While FLIT mode was required for FEC, it actually brings some really significant secondary benefits. For one, it greatly simplifies the data management logic inside the chips, but the big one is it dramatically improves bandwidth efficiency.
More efficient. Okay, how much more are we talking? Can you give us a sense of the actual improvement there?
Absolutely. FLIT mode gets rid of the old 128B130B encoding overhead that previous generations had. That was about a 1.5% tax on your bandwidth.
Right, I remember that.
PCIe 6.0 now uses what the PCI SIG calls a 1B1B encoding, which basically means there's essentially no bit-level encoding overhead anymore. They managed to spread the tiny bit of overhead across these much bigger fixed-size chunks of data. This amortization, combined with getting rid of the 128B130B tax, it means you actually get more than double the effective bandwidth of PCIe 5.0 through the pipe.
Wait, more than double, not just double.
More than double effective throughput. Think of it like switching from sending individual letters in separate envelopes to using a super-optimized express courier that perfectly packs everything into standard-sized boxes. Less wasted space, much higher throughput.
Okay, that's impressive.
It is. But this shift does have architectural consequences. It creates new hybrid operational states. It means PCIe 6.0 controllers have to be more complex because they need to support both the old variable packet way and this new fixed packet FLIT mode. Adds complexity, adds cost.
That makes sense. So going back to the FEC, if it's so critical but it's adding a new step, how did they make it work without adding noticeable delays? Because PCIe needs to be low latency, and FEC sometimes isn't.
That's a really perceptive point. Latency is paramount for PCIe. So the PCI SIG engineered a truly lightweight, very low latency FEC specifically for this. They set an incredibly aggressive target, less than 2 nanoseconds of added latency for the FEC logic itself, and they hit it.
Wow. Less than 2 nanoseconds.
Yeah. And its design is pretty ingenious, too. It uses a 3-way interleaved code. This structure makes it highly effective against burst errors, like a short blast of noise up to 16 bits long, which is a likely failure mode with noisy PM4 signals.
Okay, so it's fast and tailored to the problem.
Exactly. And this FEC is just the first stage of a 2-stage reliability strategy. First, the FEC tries to correct any errors instantly, like a proofreader catching typos on the fly. Then, a very strong 64-bit CRC check is performed on the FEC. If that check fails, meaning the FEC couldn't fix the error, then a FLT-level replay is triggered. The system just says, send that whole 256-byte block again.
Oh, okay. So FEC first, then CRC, then maybe a retry.
Right. This combination keeps the link retries the actual retransmissions exceptionally low. The target is near 0 FAC rate, failure in time, and it does all this while preserving that essential low latency profile that PCIe is known for.
Okay, so we've got this huge speed jump, PAM4, FLITs, FEC. Sounds like a lot of complex changes. Now, every great advancement comes with trade-offs. What were the big compromises or challenges they really had to navigate carefully with PCIe 6.0?
Yeah, there were definitely key trade-offs they had to meticulously manage. The big ones were power consumption, overall latency, ensuring robust security, and of course, maintaining that crucial backward compatibility.
Let's talk power first. Especially for these massive data centers, power is a huge operating cost. PM4 sounds like it would inherently chew up more power just dealing with those complex signals. How did they make this efficient?
You're absolutely right. PM4 signaling, and especially the complex equalization needed to clean up the signal, does inherently consume more power than NRZ. To counter this, PCIe 6.0 introduces a really neat feature, a new power substate called L0P.
L0P, okay.
So what L0P allows is dynamic lane-level power power scaling without interrupting data flow and without having to retrain the whole link. So imagine you have a by 16 link, but maybe right now you only need the bandwidth of a by 4 link.
Right, happens all the time.
With L0P, the other 12 unused lanes can dynamically enter a low-power electrical idle state. They essentially take a nap to save energy independently. This is absolutely vital for data centers to match power consumption much more closely to their real-time bandwidth needs. Huge potential for reducing operational costs.
Oh, that's smart. Very granular control. Okay, what about latency? With all these new layers, PM4, FEC, the FLEC-Ts having to be assembled, wasn't there a big risk of slowing things down overall?
It's a valid concern. The FLIT accumulation does add a small fixed amount of delay, that's true. But the overall latency impact of PCIe 6.0 is remarkably minimal. In fact, counterintuitively, for many common packet sizes, PCIe 6.0 can actually exhibit lower latency than PCIe 5.0.
Lower? How?
Well, because the data rate itself is doubled, and you have those efficiency gains from FLIT mode eliminating overhead. The data just gets through the pipe faster overall, offsetting the small FLIT assembly time. The PCI SIG had that aggressive target of less than 10 nanoseconds total latency adder compared to PCIe 5.0, and yeah, they successfully met that.
Okay, that's surprising, but good to hear. Now, security, it's paramount today, right?
Yeah.
Especially with all this critical data flying around. What did PCIe 6.0 bring to the table there?
Security definitely got a boost in Gen 6. Two key features here. First is integrity and data encryption, or IDE. This provides cryptographic protection for the FLITs right at the protocol level, securing data in flight against physical snooping or modification attacks on the wire.
Okay, encrypting the data on the link itself.
Exactly. And second, there's component measurement and authentication, or CMA. This uses firmware within the devices to create a kind of cryptographic signature for each component. It allows the system to verify the authenticity and integrity of the hardware, like the graphics card or the network card, before it's fully trusted and allowed onto the PCIe link. Helps prevent rogue hardware attacks.
That sounds important. And the final piece, backward compatibility.
Mm-hmm.
You invest in new PCIe 6.0 stuff. Does your older gear still play nice?
Absolutely. This is like a fundamental commandment of PCIe. Thou shalt be backward compatible.
Right.
And Gen 6 is no exception. PCIe 6.0 hardware is fully interoperable with all previous generations 1.x, 2.x, 3.0, 4.0, 5.0, all of them. So if you plug a shiny new PCIe 6.0 graphics card into an old motherboard with a PCIe 5.0 slot, it'll just negotiate down and run perfectly fine at PCIe 5.0 speeds, protects existing investments, ensures a smooth upgrade path.
Good. That's always reassuring.
Yeah. So just to wrap up this part, PCIe 6.0 isn't just PCIe 5.0 with the speed dial turned up. It's really a comprehensive re-architecture of the interconnect. It transforms it into a truly robust high-performance fabric, ready to be the backbone for, well, the next decade of computing.
Okay, so this re-architected super-fast fabric, where does it make the biggest splash? Let's start with high-performance computing, HPC. How's it unleashing potential there?
Oh, and HPC, PCIe 6.0 is a massive deal. It's truly breaking the I/O barrier that often limits large-scale scientific simulations. These simulations, they generate and consume just petabytes of data. Often the bottleneck isn't the raw compute power, it's just moving that data around fast enough.
Waiting for data.
Exactly. That 128 GBOs bandwidth from a Gen 6 by 16 link dramatically cuts down the time spent waiting for data. This means shorter simulation runtimes, which lets researchers do more iterations, tackle problems that were previously just intractable because they took too long. And it's particularly crucial for tightly coupled simulations, where consistent low latency between nodes is absolutely key.
And we're seeing more and more GPUs, specialized accelerators taking over in HPC clusters. How does Gen 6 fit into that heterogeneous world?
It plays an absolutely vital role interconnecting those next-gen accelerators and building multi-GPU fabrics. In these heterogeneous systems, mixing CPUs, GPUs, maybe FPGAs, peer-to-peer communication between the accelerators becomes critical. They need to talk to each other directly, quickly. PCIe 6.0 provides that essential system-level fabric for building really dense, high-performance multi-GPU setups.
Can you give an example?
Yeah, a prime example is something like NVIDIA's Connect X8 SuperNox. It's really innovative. It actually integrates an 800 gigabit network interface and a PCIe Gen 6 switch onto a single card.
Whoa, a switch on the NIC.
Exactly. This enables direct GPU-to-GPU communication across the PCIe fabric and direct GPU-to-network traffic, effectively bypassing the host CPU for large data transfers. GPUs can talk directly to each other or push data straight to the network without bothering the main processor. That's a huge performance gain.
Okay, so bypassing the CPU bottleneck, that's big.
It is. And from a system level in HPC, remember that L0P power state we talked about. That helps manage power efficiently in these dense, mixed compute nodes where the interconnect use might spike up and down.
Right, saving power when lanes are idle.
And there's another new feature called shared flow control. It's a protocol enhancement in FLIT mode. It basically creates a common pool of buffer credits for different data streams called virtual channels. This helps prevent frustrating head-of-line blocking where one slow stream holds up others and ensures better quality of service, especially for high-priority traffic in the simulation.
Okay, interesting. Now, let's shift gears to arguably the biggest demand driver for all this tech, artificial intelligence. How is PCIe 6.0 fueling the AI revolution?
Yeah, AI is just consuming bandwidth like nothing else. PCIe 6.0 provides the absolutely indispensable bandwidth needed for training and inferencing these massive large language models, LLMs. Training these models involves petabytes of data movement between memory and between accelerators. The interconnect is very often the bottleneck, even more so than the GPUs themselves sometimes.
Really? The pipes are the problem?
Often, yes. PCIe 6.0's 128 gigabits per by 16 link helps feed those incredibly data-hungry GPUs much faster. This accelerates training times dramatically, turning months into weeks, or maybe weeks into days. And its low latency is also vital for real-time inference, where you need those AI responses instantly. Every nanosecond counts.
That's incredible acceleration. Is there like a hidden detail, something fascinating under the hood that makes this possible for AI at such a massive scale?
Yes, there is actually. It's something that might sound minor, but it's hugely important for these large AI systems. It's the expansion of the tag field in the PCIe protocol. It went from 10 bits in PCIe 5.0 up to 14 bits in PCIe 6.0.
10 bits to 14 bits. Okay, why does that matter?
Well, those tags are used to track outstanding requests, data packets that have been sent out but haven't been completed yet. Going from 10 to 14 bits increases the number of possible outstanding requests from about 768 to a staggering 15,360.
15,000, okay.
Think of the PCIe link as this massive pipeline. The tags are like unique labels on all the data packets flowing through. Having vastly more tags means you can have many, many more data packets in flight simultaneously, waiting their turn in buffers or crossing latency gaps without causing the pipeline to stall or run dry. This is absolutely essential to actually use that massive 128 gigabits bandwidth effectively, keeping the pipe fully saturated, especially in large, spread-out AI clusters.
Ah, okay. So more tags means you can keep that huge pipe constantly full, even with network latencies and stuff.
Precisely. It prevents stalling. And this also ties directly into how PCIe 6.0 is enabling the architecture of the modern AI factory. It allows for the disaggregation of server components, separating compute, memory, storage into independent pools, all interconnected by this high-speed PCIe fabric. And PCIe switches and retimers from companies like Broadcom, Astrolabs, they become absolutely vital components in building these scalable AI systems.
This sounds like a massive ecosystem effort. How is the industry actually working together to make this complex transition happen smoothly?
It really is a huge undertaking, and deep collaboration is key. You can't have just one piece working. We've seen great examples like joint plug fests and demonstrations. Synopsys, who makes the core PCIe IP, Broadcom, a leader in switches, Micron, making cutting-edge NVMe SSDs, they get together and show their respective Gen 6 components working seamlessly together at full speed. That gives the whole industry confidence.
Right, proves it actually works end-to-end.
Exactly. The trend now is towards providing fully validated end-to-end solutions, not just silicon, but the hardware, the hypervisor software, the management tools, especially for the big hyperscalers who need these things to work reliably out of the box at massive scale.
Makes sense.
Yeah.
So, beyond the huge drivers of AI and HPC, how does PCIe 6.0 impact more general data center infrastructure, like storage and networking?
Yeah, it definitely has a big impact there, too. For storage, we're seeing a dramatic evolution in NVMe SSDs. Prototype PCIe 6.0 NVMe drives are already hitting speeds over 26, even 30 gigabytes per second. That's more than double what you get with PCIe 5.0 drives.
30 GBs from a single drive.
Wow. Yeah, it's a huge leap for those I/O-intensive database applications, big data analytics, anything that's constantly hitting storage. And a key advantage here is lane efficiency. A PCIe 6.0 drive using only 4 lanes and by 4 drive can deliver bandwidth comparable to an older PCIe 5.0 drive that needed 8 lanes.
Ah, so you free up lanes on the motherboard or server.
Exactly. Frees up valuable PCI lanes for other devices, maybe more GPUs or network cards.
But will we see these super fast drives in our home PCs soon?
Probably not mainstream for a while. The adoption trajectory for storage looks like a 2-speed track. We'll see fast adoption in enterprise and data centers where that I/O performance directly translates to value. But in the consumer market, it'll be slow, likely not mainstream until 2030 or even later. For most consumer uses like gaming or general productivity, the extra cost and complexity of Gen 6 SSDs just doesn't offer a noticeable benefit right now. PCIe 4.0 or even 5.0 is plenty fast.
Right, makes sense for gaming. Now that brings up networking. You mentioned 800 gigabit Ethernet earlier. Why is PCIe 6.0 considered mandatory for 800G? Seems like a critical link.
It absolutely is a critical bottleneck otherwise. Think about the numbers. An 800 gigabit per second Ethernet connection needs to push or pull a staggering 100 gigabytes per second of data to the host system.
Okay, 100 gigabytes for the network.
Right. But a PCIe 5.0 by 16 link, its theoretical maximum is around 64 gigabits. So PCIe 5.0 is simply too slow. It cannot feed an 800G NIC fast enough. You'd have this super fast network connection starved by a slower pipe to the server's brain.
The network would be waiting for the server. Big bottleneck.
Huge bottleneck. PCIe 6.0 by 16, however, delivers about 128 gigabits. That provides the necessary throughput with ample headroom to keep that 800G NIC fully fed. That's why leading companies like NVIDIA with their ConnectX-8, AMD with their Pensando NICs, they're building their 800G adapters on native PCIe 6.0 interfaces. It's a requirement.
Okay, that clarifies the 800G connection.
Yeah. And just briefly, the supporting ecosystem for all this includes things like retimer signal boosters, essentially, which are now pretty much essential because PAM4 signals don't travel very far on standard PCB traces, maybe just a few inches. There are also new connectors, the CEM 6.0 spec, and a big shift towards using advanced copper cables like twin-ax or even active electrical cables with built-in electronics for longer runs within servers or racks. PCB traces alone aren't always enough anymore.
Right, the signal integrity challenge. Okay, here's where, for me, it gets really interesting. We've established PCIe 6.0 is super fast, re-architected, but it's also intrinsically linked to something else called Compute Express Link, or CXL. So for our listeners, what exactly is CXL and how does it tie into PCIe 6.0?
CXL is a fascinating development. It's an open industry standard, and what it cleverly does is leverage PCIe's physical infrastructure, the wires, the signaling, the connectors, to create a high bandwidth, low latency, and crucially, cache-coherent interconnect. It connects processors, memory, and accelerators in new ways. And what's absolutely key here is that CXL 3.0 and beyond are explicitly designed to operate over the PCIe 6.0 physical layer. They use its 64 GT speed, its PAM4 signaling, its FLT-based transport.
So CXL basically runs on top of PCIe 6.0 hardware.
Exactly. CXL defines its own set of protocols that run over that PCIe physical layer. There are three main ones. CXL.io, which is basically just standard PCIe I/O for regular devices. Then there's CXL.cache. This allows accelerators, like a GPU or an FPGA, to coherently cache data directly from the host CPU's main memory. This vastly simplifies programming models for heterogeneous computing.
Okay, coherent cache, less data copying.
Right. And finally, CXL.m. This allows the host CPU to access memory that's physically attached to a CXL device. This is what enables things like memory expansion and memory pooling.
This relationship sounds really synergistic.
It's profoundly synergistic. CXL gets a mature, high-performance physical layer, PCIe 6.0, without the huge cost and time of developing its own from scratch. And in return, PCIe 6.0 gains what many consider its most transformative killer app: the ability to enable these entirely new composable system architectures through CXL. Honestly, the success of one is now deeply dependent on the success of the other. They're really like two sides of the same coin driving future server design.
Composable disaggregated infrastructure. That's a mouthful. So what does that actually mean for you, the listener, in practical terms? How does it change how data centers are built?
Yeah, it sounds complex, but the concept is powerful. It means breaking away from the traditional monolithic server model. You know, your typical server today is like one big rigid box with CPU, RAM, storage all fixed inside.
Right, a single unit.
Composable architecture allows data centers to create separate, disaggregated pools of resources. Imagine pools of CPUs, pools of GPUs, pools of specialized accelerators, pools of memory, pools of storage. Each pool is like a specialized Lego block. And they're all interconnected by this CXL fabric running over PCIe 6.0 physical links and switches.
Okay, so like building servers out of mix and match resource blocks.
Precisely. And this unlocks really powerful capabilities. One is memory expansion. Servers are no longer limited by the number of DIMM slots on their motherboard. They can access vast amounts of additional memory residing in CXL-attached memory devices.
Just adding external memory boxes.
Right. But maybe even more revolutionary is memory pooling and sharing. Data centers can create large, centralized pools of CXL-attached memory. This shared pool can then be dynamically partitioned and allocated to different servers or accelerators on demand as needed.
So like a shared community pool of RAM that any server can dip into.
Exactly like that. Instead of each server having its own dedicated RAM, much of which might be sitting idle, you have this shared pool that improves utilization dramatically. It reduces stranded memory and significantly lowers the total cost of ownership for data centers.
That's fascinating. Okay, connecting this to the bigger picture. What are the broader strategic implications of this CXL over PCIe approach for computing as a whole?
Well, by creating this unified, coherent memory space between CPUs and accelerators, it fundamentally changes how these different compute elements interact. It vastly simplifies programming models. Developers don't need to manually manage complex data transfers between the CPU's memory and the accelerator's memory nearly as much. The hardware handles the coherency.
Making heterogeneous programming easier.
Much easier. And this flexibility enables entirely new types of powerful devices and system architectures. Overall, this CXL and PCIe 6.0 partnership is set to be a critical engine, accelerating the development and performance of complex AI, HPC, and large-scale data analytics applications for years to come. It really lets us build bigger, more powerful, and more efficient compute systems than ever before.
Okay, so PCIe 6.0 is rolling out, enabling CXL in these new architectures. But I know the tech world never sleeps. The next generation, PCIe 7.0, it's already on the horizon, isn't it? Or even here.
You're absolutely right. The cadence is relentless. PCIe 7.0, the specification, was actually officially released by the PCI SIG in mid-2025. And yes, it continues that aggressive doubling trend. It pushes the raw data rate to an astonishing 128 gigatransfers per second per lane.
128 GTs per lane.
Yeah, which yields a massive 256 gigabytes per second of unidirectional bandwidth on an by16 link, and a mind-boggling 512 gigabits bidirectional throughput.
It's half a terabyte per second.
Right.
It's incredible.
It is. And what's really fascinating and strategic is the architectural continuity here. PCIe 7.0 builds directly on the foundation laid by PCIe 6.0. It retains PM4 signaling, it retains FLIT-based encoding, it retains the low-latency FEC, and, crucially, it retains full backward compatibility.
So they didn't have to reinvent the wheel again.
Exactly. This was a very deliberate choice. It leverages the substantial R&D investment already made in Gen 6, providing a much more predictable investment roadmap for the entire industry. No huge paradigm shift like the NRZ to PAM4 jump. The target applications, of course, remain those hyperscale data centers, AML clusters, HPC systems, pushing towards even more demanding requirements like 1.6 terabit Ethernet and the next generation of AI accelerators.
This just keeps going faster and faster. But it raises an important question. What happens when copper itself just hits its absolute physical limits? Can we keep doubling speeds on copper forever?
That's the critical long-term question, isn't it? And the answer is almost certainly no, not indefinitely on copper at reasonable cost and power. The PCI SIG is very aware of this and is proactively working on it. They are actively developing a standardized specification for running PCIe over optical interconnects.
PCIe over fiber optics.
Exactly. This effort aims to define a standard way to extend PCIe links using fiber optics. This would allow PCIe to break free from the severe distance limitations of high-speed electrical signaling over copper. Remember, we're talking just inches for PM4 at these speeds without help. Optics could let PCIe serve as a true rack scale, or even potentially a data center scale fabric, connecting resources much farther apart.
Okay, optics is the potential future path.
Yeah.
Now let's zoom back out to PCIe 6.0 for some strategic analysis. What does its adoption trajectory look like? Are we going to see it everywhere immediately, like in our home PCs, or is it more specialized? You mentioned the two-speed track for storage.
Yeah, that two-speed track applies broadly to PCIe 6.0 adoption. We're seeing, and will continue to see, fast adoption in the enterprise and hyperscaler markets. For them, it's becoming an absolute necessity. You need it for 800G Ethernet. You need it for the bandwidth demands of massive AML training clusters. You need it as the foundation for that CXL-based composable infrastructure we discussed. For them, the benefits are clear and immediate.
But not for consumers.
But for the consumer market, adoption will be slow, very slow. It's unlikely to be mainstream in desktops or laptops before 2030, maybe even later. The reality is, for most consumer applications today, even high-end gaming, the extra cost and complexity of implementing PCIe 6.0 just outweigh any negligible real-world performance benefit you'd actually see. PCIe 5.0, even 4.0, is more than sufficient for now.
Okay, so enterprise now, consumer later. What are the biggest hurdles the industry is facing right now with this transition to Gen 6?
The primary challenges really boil down to what some call the trilemma of cost, power, and signal integrity. They're all intertwined.
The trilemma.
PAM4 signaling and the FLIT-based architecture, they require more complex silicon designs. The chips are harder to make. You need more expensive, higher quality PCB materials to handle the signals reliably. You often need additional components like retimers on the board to boost the signal, adding cost and complexity.
Right, cost goes up.
And power. PAM4, as we said, is inherently more power-hungry than NRZ. Managing that heat and consumption, even with clever tricks like L0P, is a significant challenge, especially in dense systems.
And signal integrity.
And finally, just maintaining signal integrity at 64 gigatransfers per second is immensely difficult. The timing margins are incredibly tight. The signal is much more sensitive to noise, reflections, any tiny imperfection in the channel. It requires extremely precise engineering, meticulous board design, advanced simulation tools. It's really pushing the edge of what's possible with electrical signaling on PCBs.
A dance on the razor's edge, you said earlier.
Pretty much, yeah.
So given all this, if you're a system architect listening, or a chip designer, or maybe a product manager trying to figure out a strategy, what should you be doing right now to prepare for or navigate this PCIe 6.0 shift?
Okay, let's break that down. For data center and HPC architects, the clear message is embrace composability. Start designing and planning with CXL in mind. Also, rigorously evaluate integrated solutions. Things like those NACs with onboard PCIe switches can simplify designs, and definitely focus on fully validated end-to-end solution stacks to minimize deployment risk. Don't try to piece everything together yourself from scratch unless you have to.
Okay, architects. Think CXL, integration, validation. What about chip designers?
For the SoC and chip designers, given the sheer complexity, seriously consider prioritizing buy over make for the core PCIe 6.0 IP block. Building and verifying this stuff is incredibly resource intensive. Focus your differentiation efforts on power performance area, PPA optimization. How can you make your implementation lower power? How can you optimize features like L0P? And crucially, plan for CXL integration right from the start. It's not an afterthought. It's central to the value proposition.
Got it. Buy IP, optimize PPA, integrate CXL. And for product managers?
For product and marketing managers, you need to tailor the message. For the enterprise market, shift the value proposition. It's not just about raw speed anymore. Emphasize the new architectures enabled by PCIe 6.0 and CXL. Talk about lane efficiency, AI density, composability, TCO benefits. For the consumer market, manage expectations carefully. Position PCIe 6.0 as future-proofing, maybe for high-end enthusiasts, rather than an immediate must-have performance boost for everyday users or gamers today. Be realistic about the timeline and the benefits.
That's great advice. Okay, so there you have it. A really deep dive into PCIe 6.0. It's clearly so much more than just a speed upgrade. It's really a foundational redesign of the very backbone of computing. From that ingenious, if challenging, shift to PAM4 signaling, to the efficiency gains of FLIT mode and that critical low-latency FEC, it's all been meticulously engineered to meet these absolutely insatiable demands of AI, HPC, and the modern data center.
It's truly fascinating when you dig in. You see how these seemingly minute technical details like, expanding a tag field from 10 to 14 bits or creating a dynamic power state like L0P, how they collectively unlock entirely new paradigms. PCIe 6.0, especially working hand in glove with CXL, isn't just connecting components faster. It's enabling this profound shift away from rigid monolithic servers towards these dynamic, composable AI factories. It really transforms how we think about building and scaling computational power, offering levels of flexibility and efficiency we just haven't had before.
That's a lot to mull over, definitely. And it raises, I think, an important question for you, our listener, to think about. How will this fundamental shift, moving away from traditional server architectures towards these disaggregated, composable AI factories built on technologies like PCIe 6.0 and CXL, how will that truly change computing as we know it over the next 5-10 years? And maybe more excitingly, what completely unexpected innovations might emerge from this new, incredibly flexible infrastructure in the years to come? This was another deep dive, designed just for you. Thanks for joining us.